Section 1. The Unlikely Masters of the Sky. Imagine a vast, sun-baked landscape. The air shimmers with heat. Nothing seems to move. But look closer. High above, a dark shape circles. It hangs almost motionless against the brilliant blue sky. This is a vulture. It is a creature often misunderstood, linked with death and decay. Many people see them as grim omens. They are large, dark, often seen gathered around the fallen. Yet, this perception, this story we tell ourselves, misses the true marvel of these incredible birds. They are not just scavengers. They are masters of an invisible world, a world of air currents and energy. Their appearance is striking, almost prehistoric, with their broad wings, often spanning over 2 meters, their bald, featherless heads. Every feature is a masterpiece of evolution, honed over millions of years for a very specific, vital purpose. Their role in the ecosystem is crucial. They are nature's cleanup crew, the ultimate recyclers. Without them, disease would spread much more easily across the plains and forests they call home. They are a cornerstone of a healthy environment. But how do they do it? How does such a large, heavy bird stay aloft for hours, often without a single flap of its wings? It seems to defy the very laws of physics. A bird that can weigh up to 15 kilograms should, by all rights, struggle to even get off the ground. Yet they soar with an elegance that smaller, lighter birds can only dream of. They ride the air with a grace that seems impossible for their size. This is the central paradox of the vulture, the question that has fascinated scientists and observers for centuries. They simply shouldn't be able to fly the way they do. In this journey, we will look beyond their reputation. We will set aside the myths and uncover the extraordinary reality. We will explore the vulture not as a symbol of doom, but as a triumph of biological engineering. This is a story of incredible efficiency, of hidden adaptations, and of a deep connection to the forces of nature. We will see them as they truly are, the unlikely and undisputed masters of the sky. Their flight is not magic. It is a beautiful and complex dance with the wind, a performance perfected over countless generations of survival in some of the world's harshest environments. Section 2. A puzzle of physics and flesh. At first glance, the vulture's flight seems to break all the rules. To understand this, we must first think about what it takes for any object to fly. The principles are simple, yet profound. An aircraft or a bird needs to generate a force called lift, which pushes it upwards. This lift must be strong enough to overcome its own weight, the force of gravity pulling it down. At the same time, it must fight against drag, the resistance of the air that tries to slow it down. To move forward and create that lift, it needs thrust, a forward-pushing force. But soaring vultures don't seem to have an engine. This is where the puzzle begins. A flapping bird generates its own thrust, using its powerful chest muscles to beat its wings against the air. But a soaring vulture is doing something entirely different. It is a glider. It is using the energy already present in the atmosphere to stay airborne. This is a much more efficient way to travel, saving enormous amounts of energy. But it requires a deep, intuitive understanding of the air itself. The vulture has to find and exploit invisible pockets of rising air, columns of warm air called thermals, or air deflected upwards by ridges and mountains. To solve this puzzle, we are going to dive into the world of physics and biomechanics. We will look at the numbers and the equations that govern flight. We will not shy away from the mathematics. Instead, we will use it as a tool to unlock the vulture's secrets. We will calculate the forces acting on a vulture's wing. We will explore concepts like glide ratio, which tells us how far a bird can travel horizontally for every meter it descends. We will also examine wing loading, the ratio of a bird's weight to its wing area, which is crucial for understanding its soaring capabilities. This journey will be supported by a wealth of archival materials. we will bring to life the work of early pioneers in aerodynamics and ornithology who first began to study these magnificent birds. We will unearth old photographs, forgotten scientific papers, and dusty museum specimens. These historical documents provide a unique window into how our understanding of vulture flight has evolved over time. By combining cutting-edge science with a look into the past, we can piece together the complete story of how these birds achieved their seemingly impossible feats of aerial grace. Section 3. Our promise: uncovering the secrets. Our investigation will not stop at the physics of the air. We must also look at the vulture itself: body, bones, feathers. This is a story of biomechanics. The vulture's body is a marvel of adaptation. Every part, tip of the beak, end of the tail feathers. We will explore these hidden adaptations. We will focus on the vulture's wings. Their shape is not arbitrary. Long, broad structure. How that shape captures the slightest lift from the air. We will look at their feathers. Slotted primary feathers at the wingtips. They act like winglets on a modern airliner, reducing drag and improving stability. We will venture inside the bird. Animations. Models. To compare bone structure to other birds. You will see how their bones are strong yet surprisingly lightweight. A perfect compromise between durability and the demands of flight. But the adaptations go far beyond flight. We will also investigate the vulture's remarkable head and neck. The bald head isn't just for show, it's a critical adaptation. For a bird that feeds by putting its head inside carcasses, keeping it clean and free from bacteria, we will examine the biomechanics of its powerful beak and the incredible flexibility of its long neck. Furthermore, we will delve into its digestive system, a fortress capable of neutralizing pathogens that would be lethal to almost any other creature on Earth. This internal armor is just as important as its wings. In this documentary, we promise to bring you a rich and exciting narrative. We will use a variety of visual techniques to make this complex subject clear and engaging. Expect stunning high-definition footage of vultures in their natural habitat, the plains of Africa, and the mountains of the Andes. We will use clear graphics and animations to explain the physics and biomechanics in simple terms. We will overlay archival footage and historical documents. This will be a visual spectacle, a journey revealing the hidden genius of a creature that truly shouldn't be able to fly, but does. Table of Contents, Part 2, Act 1, The Sky and the Laws. Section 1, The Four Forces of Flight. Section 2, The Glide Ratio, a measure of efficiency. Section 3, Wing Loading, the burden of being big. Section 4, The Reynolds Number, navigating the air's stickiness. Section 5, The Invisible Engine, riding on thermals. Section 6, The energetic cost of staying aloft. Section 1, The Four Forces of Flight. To understand how a vulture stays in the sky, we must first understand the sky itself. It is not empty space. It is a fluid, an ocean of air with its own currents, waves, pressures. And for any object to fly within this ocean, it must contend with four fundamental forces. These forces are in a constant battle, a delicate balancing act that determines whether something rises, falls, or soars. Imagine a vulture, suspended high above the ground. It is being pulled downwards by its own weight, the relentless force of gravity. This is the first and most obvious force, the one that every flying creature must fight against. To counter its weight, the vulture needs an upward force. This is called lift. Lift is a magical seeming force, generated when air moves over a specially shaped surface, like a wing. The curved upper surface of a vulture's wing forces air to travel faster than the air moving along the flatter bottom surface. According to a principle discovered by the Swiss mathematician Daniel Bernoulli, faster-moving air has lower pressure. This pressure difference, with higher pressure below the wing and lower pressure above, creates a net upward push. This is lift. For a vulture to maintain its altitude, the lift generated by its wings must be equal to its weight. But the air also resists motion. This resistance is called drag. It is the force that you feel pushing against your hand when you stick it out of a moving car's window. Drag is the enemy of efficiency. It constantly tries to slow the vulture down, pulling it backwards. To fly, a bird must overcome this drag. For a flapping bird, the force used to overcome drag and move forward is thrust. This is generated by the powerful downstroke of its wings, pushing air backwards to propel the bird forwards. For a soaring vulture, however, there is no flapping, no obvious engine providing thrust. This is the heart of the mystery we must unravel. So, we have this constant tug of war. Weight pulls down while lift pushes up. Drag pulls back while thrust pushes forward. For a bird to fly at a constant speed and altitude, these forces must be in perfect balance. Lift must equal weight, and thrust must equal drag. The genius of the vulture is its ability to manipulate these forces with incredible precision and minimal effort. It has mastered the art of generating enormous lift while creating very little drag, and it has found a way to generate thrust not from its own muscles, but from the energy of the atmosphere itself. It is a physicist in feathers, constantly solving this four-part equation. Section 2. The glide ratio. A measure of efficiency. How do we measure the efficiency of a glider, whether it's a paper airplane, a high-tech sailplane, or a vulture? One of the most important measures is the glide ratio. This is a simple but powerful concept. It tells us how far a gliding object can travel forward horizontally for every unit of height it loses vertically. Imagine a vulture is gliding from a height of 1 kilometer. If it has a glide ratio of 20:1, it means it can travel an impressive 20 kilometers forward before it reaches the ground, all without a single flap of its wings. This number is a pure measure of aerodynamic efficiency. Let's look at the mathematics, which is surprisingly straightforward. The glide ratio is simply the amount of lift a wing generates, divided by the amount of drag it creates. We can write this as an equation. Glide ratio equals lift divided by drag. A high lift-to-drag ratio means the bird is very, slippery in the air. It can slice through the atmosphere with minimal resistance, converting its altitude into forward distance with remarkable effectiveness. For comparison, a commercial airliner might have a glide ratio of around 17:1. A high-performance sailplane can reach 60:1. A turkey vulture, one of nature's most efficient soaring birds, has been measured with a glide ratio of up to 23:1. Animation. Two birds gliding, one descends steeply, the vulture travels much farther with 23:1 displayed. This exceptional efficiency is not an accident. It is the result of millions of years of evolution shaping the vulture's wing. Long, broad shape, the specific curvature of the airfoil, the slotted feathers at the wingtips, all work together to maximize lift while minimizing drag. This allows the vulture to cover vast distances in search of food. A carcass might be many kilometers away, and the vulture needs to be able to get there without expending precious energy. A high glide ratio means it can survey huge areas of land from a great height, slowly and methodically descending as it searches, confident that it can travel a long way before needing to find another source of lift. So, when we see a vulture circling, it is not just floating aimlessly. It is engaged in a calculated process of energy management. Every moment it spends in the air is a testament to its high glide ratio. It is constantly trading potential energy, its height, for kinetic energy, its forward motion. It is a master of this conversion. The higher it can get, the more ground it can cover. Its ability to stay aloft for hours is directly tied to this incredible aerodynamic efficiency. The glide ratio is the secret number that underpins its entire lifestyle, a number that evolution has pushed to a remarkable extreme, making the vulture a true champion of gliding flight. Section 3. Wing loading, the burden of being big. While a high glide ratio explains the vulture's efficiency, it doesn't explain how such a large, heavy bird can soar so well on weak air currents. To understand that, we need to introduce another crucial concept: wing loading. This is a simple ratio of the bird's total weight to the total area of its wings. You calculate it by dividing the weight of the bird by its wing area. So the equation is wing loading into weight wing area. This number tells us how much weight each square meter of the wing has to support. A bird with low wing loading feels light for its size, while a bird with high wing loading is heavy for its size. Let's put some numbers to this. A small songbird like a sparrow might have a wing loading of about 15 newtons per square meter. It is light, with relatively large wings for its body, allowing it to be agile and take off quickly. Now consider a Ripple's griffon vulture. It can weigh up to 9 kilograms, and its wings have an area of about 1.2 square meters. Its wing loading is therefore much higher, around 75 newtons per square meter. This high wing loading presents a challenge. It means the vulture needs to fly faster to generate enough lift, and it makes taking off a much more difficult and energy-intensive process. So why have high wing loading at all? It seems like a disadvantage. However, it comes with a significant benefit, especially for a large soaring bird. A higher wing loading means the bird has more momentum and is less affected by turbulence. It can fly faster and more steadily in windy conditions, penetrating through gusts that would toss a lighter bird around. Furthermore, a high wing loading allows for a higher maximum gliding speed. This is crucial for a vulture that needs to travel quickly between a thermal and a potential food source. It sacrifices low-speed agility for high-speed, long-distance stability and efficiency. This is the trade-off that evolution has made. Vultures are not built for darting through forests like a sparrow. They are built for the open sky, for covering vast, empty landscapes. Their high wing loading makes them less adept at slow, tight circling in very narrow thermals, but it makes them supreme masters of cross-country travel. They are the long-haul trucks of the avian world, optimized for stability and speed over long distances. Understanding wing loading shows us that the vulture's size and weight are not just a burden to be overcome. They are an integral part of its strategy for dominating the skies. Section 4. The Reynolds number, navigating the air's stickiness. Our journey into vulture physics takes us to a concept that might seem obscure, but it's essential for understanding flight at different scales. This is the Reynolds number. In simple terms, it tells us how air behaves when an object moves through it. It's a ratio that compares inertial forces to viscous forces. A low Reynolds number means the air feels thick and syrupy, like honey. A high Reynolds number means the air feels thin and fluid, like water. Visual scale: gnat, low Re; vulture, medium-high Re; airplane, high Re. The equation looks complex, but the idea is simple. Re, 1, rho, v, L, mu. Rho is the density of the air. V is the speed of the object. L is a characteristic length, like the width of the wing. Mu is the viscosity of the air. For a tiny insect, speed and size are very small, so its Reynolds number is low. It flies as if it's swimming through molasses. Drag is a huge problem. For a large, fast-moving jumbo jet, the Reynolds number is enormous, in the millions. For the jet, the air feels thin. Inertial forces dominate. Where does the vulture fit in? A vulture is large and flies relatively fast. It operates at a high Reynolds number, typically in the hundreds of thousands. That's a sweet spot for flight. The air behaves predictably and non-sticky. This allows smooth, stable flow over its wings, essential for consistent, efficient lift. The flow is less likely to break up into turbulent, drag-inducing eddies. In this high-ray regime, the beautifully shaped airfoils of a vulture's wing can perform their magic. If a vulture were the size of a beetle, its wings simply wouldn't work the same way. The Reynolds number also helps explain the slotted feathers at the Vulture's wingtips. At lower speeds, when the Vulture is circling tightly, the Reynolds number over parts of the wing decreases. That increases the risk of airflow separating from the wing, causing stall and loss of lift. The slots between the primaries act as multiple small, high aspect ratio wings. Each one operates at its own Reynolds number, helping maintain smooth airflow and prevent wingtips from stalling. It's a brilliant, passive aerodynamic control system that lets Vultures push low-speed flight without losing control, crucial when staying in a narrow column of rising air. We've established that the Vulture is an incredibly efficient glider, but gliding is, by its nature, a descent. To stay airborne for hours, the Vulture must regain the altitude it constantly loses. It needs an engine. But its engine is not made of muscle and sinew. It is made of air and sunlight. The Vulture's primary power source is an invisible phenomenon known as a thermal. A thermal is a rising column of warm air. As the sun beats down on the ground, it heats different surfaces at different rates. A dark, plowed field will get hotter than a green forest or a body of water. This patch of hot ground heats the air directly above it. Hot air is less dense than cool air, so it begins to rise, like a hot air balloon without the balloon. This rising bubble or column of air is a thermal. For a soaring bird, a thermal is an elevator. By finding and circling within this column of rising air, the Vulture can gain height without flapping its wings. The air inside the thermal is rising faster than the Vulture is sinking through it, so the net result is a steady climb. The Vulture effectively gets a free ride to a higher altitude, refueling its potential energy, which it can then convert back into distance through gliding. Finding these thermals is a skill honed by experience and observation. Vultures are masters at reading the landscape and the sky to predict where thermals will form. They watch for subtle clues, like the formation of cumulus clouds, which often mark the top of a strong thermal. They also watch each other. If one Vulture finds a thermal and begins to circle upwards, other Vultures from kilometers around will see it and converge on the same spot. This creates a kettle of Vultures, all sharing the same invisible elevator to the sky. It is a remarkable example of social cooperation to exploit an environmental resource. Besides thermals, Vultures use another form of free energy called ridge lift. When a steady wind blows against a hill, a ridge, or a mountain, the air is forced to flow up and over it. This creates a band of rising air along the windward slope of the ridge. Vultures can soar back and forth along this slope, riding this upwardly deflected air for hours, again without needing to flap. By skillfully switching between thermals over the plains and ridge lift in hilly terrain, the Vulture can navigate vast and complex landscapes using only the power of the wind and the sun. It is a solar-powered bird, a true master of atmospheric energy. Flight is the most energetically expensive form of locomotion. For any bird, taking off and flapping requires a huge amount of power, burning through calories at a tremendous rate. For a large, heavy bird like a Vulture, the cost of flapping flight is almost prohibitively high. Scientists have measured the metabolic rate of birds in flight, and the numbers are staggering. A flapping Vulture would burn energy at a rate many times higher than its resting metabolic rate. It simply could not find enough food to sustain this level of activity for very long. This is the ultimate reason why Vultures are so dependent on soaring. Soaring is the Vulture's solution to this energy crisis. By using thermals and ridge lift, the Vulture can reduce its energy expenditure during flight to a level that is remarkably low. Studies using heart rate monitors on free-flying Vultures have shown that the energy cost of soaring is only slightly higher than the energy cost of sitting on a perch. It is an incredibly efficient mode of transport. The bird expends a burst of energy during the initial takeoff, which is a strenuous, flapping and running affair. But once it finds its first thermal and gains altitude, the hard work is over. The rest of the day can be spent gliding and soaring with only minimal wing adjustments. This low-energy lifestyle dictates the vulture's daily routine. They often wait until mid-morning to take flight. They are not being lazy. They are waiting for the sun to heat the ground sufficiently to create the strong thermals they need to get airborne efficiently. Taking off too early would mean more flapping and a greater waste of precious energy. This is a bird that lives on a tight energy budget. Its food source, carrion, is unpredictable and scattered. It cannot afford to waste energy on an inefficient search pattern. Soaring allows it to survey the maximum possible area for the minimum possible cost. Ultimately, the physics of vulture flight is a story of economics. It's about balancing an energy budget. The lift, drag, glide ratio, and wing loading are all just factors in a grand equation of survival. The vulture's body and its behavior have been exquisitely shaped by the need to solve this equation every single day. By harnessing the free, invisible energy of the atmosphere, the vulture has turned a seemingly impossible challenge, powering a 15-kilogram body through the air for hours on end, into a model of efficiency. If you were to design the perfect wing for soaring, you would likely end up with something that looks very much like a vulture's. The shape of a bird's wing is its most fundamental aerodynamic tool. It is the architect's blueprint, defining how the bird will interact with the air. Vultures, especially the large griffins. Condors. This general shape is often described as a high-lift wing. It is not designed for high speed, like the narrow pointed wings of a falcon. Top-down silhouette comparison of swift, sparrow, and vulture wings labeled with flight styles. Instead, it is designed to generate the maximum possible lift at relatively low speeds, which is perfect for circling slowly in a column of rising air. The broadness of the wing is crucial. A wide wing, from its leading edge to its trailing edge, creates a large surface area. As we saw when discussing wing loading, a larger wing area helps to support a heavy body. But the width, or chord, of the wing also gives it a deep, curved profile. This curvature, known as camber, is what forces the air to accelerate over the top surface, creating the pressure difference that generates lift. The deep camber of a vulture's wing is like a powerful scoop, grabbing hold of the air and converting its movement into upward force with remarkable efficiency. This allows the vulture to stay aloft even when the upward movement of a thermal is quite gentle. This design, however, comes with a trade-off. A broad, deeply cambered wing also tends to create more drag, especially at higher speeds. This is why vultures are not the fastest birds in the sky. Their design is a compromise, optimized not for a sprint, but for an endurance marathon. They have sacrificed outright speed for the ability to hang in the air with minimal effort, to loiter. This ability to stay airborne for long periods, slowly scanning the ground below, is far more important for a scavenger than the ability to chase down fast-moving prey. The wing shape is a direct reflection of the vulture's patient, watchful, and opportunistic lifestyle. So when we look at the silhouette of a vulture against the sun, we are seeing more than just a bird. We are seeing a solution to a complex engineering problem. We are seeing a shape honed over millions of years to perfectly exploit the physics of the air. It is a shape that says, I am built to wait. I am built to watch. I am built to ride the invisible currents of the world with the least possible effort. The wing is not just a limb, it is the physical embodiment of the vulture's survival strategy, a masterpiece of natural design forged in the crucible of the open sky. Section 1. A Symphony of Science. We began our journey with a simple paradox, a creature so large and heavy that seems to hang in the sky as if by magic. We have seen that there is no magic, only a profound and elegant application of physics and biology. The vulture's flight is a symphony of science, where every note is perfectly played. We have dissected this performance piece by piece. We have explored the four fundamental forces of flight: lift, weight, drag, thrust, and seen how the Vulture manipulates them with an efficiency that rivals our own best aircraft designs. It is a master of the invisible world of air currents. We have translated its physical form into the language of mathematics. Glide ratio, wing loading, Reynolds number. These numbers are not just abstract concepts. They are the rules by which the Vulture lives and flies. From the sky, we dove into the bird itself. We saw how the shape of its wings, their moderate aspect ratio, and their slotted primary feathers are all a perfect compromise between long-distance gliding and the tight maneuvering needed to ride a thermal. We ventured inside, discovering the miracle of its hollow, strut-reinforced bones and its fused, rigid skeleton, an airframe built for maximum strength at minimum weight. Every element of its anatomy, from the large-scale form of its wings to the microscopic structure of its bones, has been honed by millions of years of evolution for one purpose: effortless flight. We discovered the genius of its bald head, marveled at its long, flexible neck, and examined its powerful, hooked beak. We then ventured into the Vulture's inner world, a place of chemical warfare and biological fortitude. We learned of its stomach, a caustic fortress, and saw how its immune system and unique gut bacteria provide a second and third line of defense, making the Vulture a true dead end for disease. As nature's cleanup crew, they work tirelessly and efficiently to remove decaying carcasses from the landscape. By doing so, they prevent the spread of diseases like anthrax and rabies, protecting other wildlife, protecting livestock, protecting human populations. For too long, these magnificent birds have been misunderstood and persecuted. But as we have seen, the truth is far more impressive. They are not grim reapers, but unsung heroes. They are masters of physics, marvels of biology, and guardians of the environment. The Vulture deserves not our scorn, but our admiration and our protection for the vital and beautiful role it plays on this planet. Section 3, Your Place in the Story. The technology that allowed us to follow these birds is also a tool for their salvation. The science that helps us appreciate them is also the science that can help us save them. But the story does not end here, with us. It continues with you. By watching this, you have become part of that story. We hope this film has given you a new perspective on these masters of the sky. And so, if you found this journey into the physics and biology of the Vulture as fascinating as we did, please help us to share these stories with more people. Give this video a like to let us know you enjoyed it. Channel logo graphic with like and subscribe buttons highlighted. And if you want to join us on more journeys into the amazing science of the natural world, please subscribe to our channel. There are so many more secrets to uncover, so many more marvels of engineering to explore in the animal kingdom. Thank you for watching.